Good. It works. My test. Okay, good. Let's get started. Any questions about anything? Okay. Right. So let me just give you a brief review of what we talked about, and then I will move on. Basically, I derived the formula for differential transition probability. All right. Starting from the discretization. Well, I finished the discussion of what did I do? I finished discussion of a crossing, and then I talked about the CPT, right? Some aspect of CPT, and then I discussed the differential transition probability, which I will give you some brief review. Okay, and then the goal of today's discussion is we will spend some time to use the general formula that we derived, differential transition probability, to talk about decay and then scattering with the two particles in the initial state. Okay? Good. So then after that, we will switch gears a little bit to talk about an object called the Green's function and generating functional. And then hopefully we will finish up the discussion by discussing LSD reduction formula, which, in a sense, clearly and precisely connect the Green's function, how to extract asymmetries from the Green's function. So that will be the discussion. And so today is Wednesday, and Friday we will have a one makeup at 5 p.m. Okay, so no makeup in the morning at 5 p.m. Hopefully you can get out. We'll see. And then the schedules for the later week, next week, we will post. I will post, okay, real time. But you already saw TA summarized the plan for the makeups, and I think I might need. We'll see if I need all of those makeup lectures, or I need only a few. We'll see. So I will let you know how things go. Good. So therefore, I will review briefly the derivation of differential transition probability. So I'm about to do it. But before that, any question on any aspect? Yes.
The crossing symmetry we talked about last time. Yeah, my question last time, it wasn't like two particles that goes into one particle of the decay. It's like three particles. Is it possible if we switch the time direction so that three particles goes into that?
1, 2, 3, and vice versa. That thing you're talking about.
Yeah.
Okay. Yeah. So if I understood it correctly, the question is, last time we focused on the case where there's a blob with a 4-particle length, and then I mostly talked about 2 to 2 to 2 to 2. Your question is there a notion of a crossing? If I just look at the 1 to 3, there is a certain connection between 1 to 3 to 3 to 1. That should be clear, right? Basically, time reversing modular kinematic factors. But are there any other crossing channel? So there, I'll say that you have a in momentum consisting of 1, out momentum consisting of 3, for instance, right? So let's see. So now we're talking about something like this. I mean, you can take the same convention. So you're asking this question, right? But you see, the idea of crossing is that given, so this diagram, I could have done a slightly different thing. Let's see. So suppose I had this actually, a lot of them. And then I take this cluster as a one sort of asymptotic state. This consists of another asymptotic state, another asymptotic state, another asymptotic state. Then the crossing was, I can change the role of in versus out, right? By sending P to minus P. So here I have a cluster of a state that I can identify as an asymptotic state, and there's another one. Although, okay, obviously they will split. Now, your question, if I understood correctly, can I look at another channel? Is it sensible to take this as a one say, out state, reverse this to in state, and is there any relation between this decay and then that channel? For instance, you don't like the way I rephrase your question? I guess we can check it at least for this at tree level explicitly. Okay, if we write down a theory, so suppose I write down theory like this. So there's a one heavy guy and possibly decay to 3 light guy. In decay, we can write down easily. If there's a local vertex, the decay will be, so amplitude for phi to psi q will be just minus IG. IG. So if this is G, right? That's it. There's no propagator involved in this thing. Then you can ask, okay, how is it related to amplitude of phi go into, for instance, like a phi this, right? And okay, maybe this is too trivial, and this is my answer. Same analytic function of ST, right? I'm not lying. I'm serious. No? So this is the phi. Sine. So maybe this is too trivial. Let's see. Can I come up with some non-trivial theory to check it? Okay, let's see. So since I don't have an immediate answer, that's why I'm playing with it. You see, right? What else? So let's check another one. Okay, so let's consider phi squared eta. All scalars. Okay, we love scalars. So one amplitude so this is a heavy guy, this is 2 light guy, possibly different mass. We can talk about this. So now I need to invent. So one heavy guy, 2 psi, and then eta. Right? Okay. Would this be also completely trivial? Okay, probably. Okay, I'll just give you an exercise. So for instance, you can, I think, you can consider theory like this to make it slightly less non-trivial. So if you start talking about this local operator, I think you will get trivial the same answer. This is a single local vertex. So for instance, if I consider this theory instead, and then if you want to ask a question of decay into psi q, then you have to do things like this. So it's a phi, and then you split into eta, and then eta can split into this. So now there's at least a propagator which will give you non-trivial function of ST. Okay? And then you can ask in this thing, what if I instead ask that question versus psi square, psi going into psi plus phi. And in this example, modulo the other channels you also have to draw carefully. For this diagram, obviously we get the same answer, right? So if you flip, now you interpret this as initial state, you will have a propagator, flip it back into. So obviously these two amplitude for this particular diagram must be the same. So it does satisfy the crossing relation if you wish. Okay? So I might not even conclude that indeed it does satisfy the relation. Yeah. But let me know if you discover non-trivial loophole that I'm missing.
No, I guess this is
okay. Maybe this can be final
because the blog makes me feel like there are something non-trivial loop thing inside. So
very good.
That's good.
Yeah. The crossing is good. So let me say this. So the crossing property that discussed. All the examples I took was only tree level processes, right? Because we only learned how to deal with the tree level. And we haven't developed the machinery to compute the loop diagrams. We don't know how to think about it yet. So, and then we saw, at least for those examples that we considered, we saw nicely that all the crossing properties satisfied. But obviously the statement is that it should be true to all orders in perturbation theory. So including not only the pole singularities, branching co-singularities, it will still satisfy the crossing relations. Okay? Now, so therefore, starting from this, I would have felt that it should work. Now I'm more convinced it should work because, I mean, I could have set up the discussion of n particles, right? And so I could have set up the discussion with the n particles, and then I could have set any choice of a number of them taking as in state, the rest as out state, should have those crossing properties. And this is just one particular example where you take one as initial and the other as a final, versus you take a different step, right? So this single amplitude, the point was, if I can construct an amplitude for this one without specifying which ones are in, which ones are out, there's one given meromorphic function of a SDU. In this case, you will have more variables because you have a more kinetic momentum. But that amplitude should describe the different processes, which are all given by this. So this should be a peculiar example, one particular example of that. So now I'm more confident. Yes, it should work. Yeah. Good. Who knows? This kind of period finally. Any other questions? Okay. So then let me start today's discussion by again giving you some review of a discussion we had last time. So last time we talked about differential transition probability, right? Very quickly by first discretizing it. So if you recall, this thing had a unit of 2 pi q delta q to e. And I told you that this thing has the same dimension of the space volume, right? And so we could have defined this relativistically invariant or covariant normalization to a dimensionless quantity by basically taking into account these dimension factors. And now this will be my dimensionless creation annihilation operators. And then, so that was the discussion number one. And then we wanted to basically define this object. So there's a final, and then S matrix, not only including non-trivial column, initial, but in terms of a dimension is possible, as dimension is possible, the state. So these are related by, for instance, I want to define for instance, this will be my one particle state, but without carrying any dimension with it. And then the motivation was that as I consider different number of final state, even the initial state we might specify the number of particles, I want to have a formalism where this still captures the transition probability amplitude, even if I take a different number of particles, right? So that was the motivation. Then you just need to know how to relate the normal Fox space state defined in terms of this, and also the state, in this case the discretized version of the state, which doesn't carry dimension. So that's already clear in that. So if I consider relativistically, I should be careful. Relativistically invariant. But that's not invariant, it's covariant. But I shouldn't change NR. Why was NR what? But still, I have this inertia. I couldn't solve that problem. If somebody can solve the problem, let me know. This is related to this discretized state. Okay? Literally, basically, this relation. So, or you can just use the fact that whenever you see discretized a single state, you want to write it as 1 over v, square root of v, 1 over square root of 2e, and then a normal relativistically this. Okay? Now, and then I said the following thing. So final state, you should treat it state as a really probabilistic in nature, right? So you prepare initial state, boom, something happens, and then a different final state can be produced, sometimes and oftentimes even different number of final state particles. So for each, so for instance, if you want to consider P1, P, N, F final state, then basically you need to put this compared to relativistically invariant normalized. Oh, this is normalization. Sorry, I shouldn't thinking about it. This thing, normal state, right? So for final state, for each particle state, assuming this is asymptotic state, so which is factorized into product of a free particle state, you just have this factor. However, for initial state, initial, am I correct? Am I doing well? Initial, okay, thank you. Initial state, we have to think a little bit more, okay? So for initial state, we will consider only two cases. The first case, number of initial state being just one. This case, we're talking about decay, right? So we just prepare one particle, let it do whatever it does, decay to something else. And then we are going to consider scattering process. So we just prepare two initial states, and let them collide and see what happens. Here, the point was that we will prepare initial state with the probability 1, meaning we know what's happening there. So if we talk about the single particle initial state, so say P and D initial state, we just literally do this. Okay, no funny business. But then there was something to be checked still. So to see why this formula is good, we can check that probability in this discretized version. I want it to be 1. So if you do that, you get 1 over V, 2E, let me drop P. And then using the relativistically invariant normalization, you also get, instead of V, let me just write delta, and then 2E. So I said that, okay, let's forget about the 3 factor. We can interpret this is basically summing over entire space volume, which means that this formula is same as there's a 1 over V probability to find that particle anywhere in this position. But since you are summing over entire space, you should get the probability number 1, which means that there's a 100% probability chance to have the particle somewhere in the space. Okay, so that was the interpretation. So for one particle state, that's what we do. So we prepare particles somewhere in the space, let it decay, and then see what happens. However, if we want to talk about two particles in initial state, okay, so naively, this will have a product of 2. So we will have this for the first particle, and then we will have this for the second particle, P1, P2, this. And then I say that this is not so good. So this is like saying I throw in the first particle with the probability 1 over V, and then I also throw a second particle probability 1 over V somewhere. And then if you compute the normalization, in this sense, you will not get 1, right? In fact, you will get 1 over V, meaning as you send the V to infinity, you get 0 probability. What that means is that if you just randomly throw out the two particles in the space, obviously there is very little chance for them to actually meet and collide each other. So in order to avoid that, therefore, in order to actually prepare final state, initial state, such that we know that they will have a 100% chance to collide each other, so I first throw out the one particle somewhere in the space, and then I have to basically throw out not one particle, but V number of a second particle, so that there's a 100% chance to collide. So therefore, we said that the final state we prepare actually is square root of V times this naive version. So that was what we talked about. So with that preparation, now we went on and constructed the transition probability. Transition probability. So therefore, differential transition probability can be written as basically we looked at a final state, initial square. So that gives a probability modulo this a bit of a dimension factor. Remember, this is dimensionless factor, right? So for the decay, this is a genuinely dimensionless quantity. For scattering, that object will have a dimension according to this dimension, square of this dimension, right? Because it is initial state carry now non-trivial dimension. But modulo that, this is a probability starting from prepared initial state turning into a fixed momentum configuration of final state. So once you specify final state with the momentum configuration fixed, this will give you actually the probability for that particular transition to happen. But then we say that final state can take any sort of allowed kinematics. So then we say that we have to actually sort of multiply final state density of state. So in other words, what is the number of a state for a given final state particle jumping into a particular solid at angle of 3 momentum? Right? That's the question. And then this, by just using p times l is equal to 2 pi integer, can be computed as this is nothing but integral v3p times v. Okay, so cube this, we get this. Okay, so good. So then you can combine everything together. Eventually, we arrive at the fact that now this is a t. Okay, if you just compute things, t times we get. Let me just write initial factor first. So initial, you multiply by this. Okay, according to that discussion. Why 1 over 2e rather than 1 over square root 2e? Because here you have to square that. So each factor gets squared. Okay, so this is why you got 2e. And then you have this Feynman invariant amplitude square. And then you have this total final, total initial. And then for each final, you do I have to space. So that was the final answer we arrived. Okay? And then I just define this to be this of f. So this is relativistic density of state. Okay, what is number of states of the final state? And so if you are interested in transition, differential transition probability per unit time, I just wait 1 second and then what's the probability for that particular process to happen? You can divide it by t, so that will be the answer. Okay, so from this to that is our expression for differential transition probability per unit time. Okay. So that's the sort of a quick summary of what we did last time. So let's continue from this. So now we can actually consider 2 cases separately. So let's talk about the decay. Okay? So in this case, I'm interested in some amplitude where one particle turning into some nf number of final state particles. Okay? So that's what we do. So let's actually write down. In the decay, we're going to write it as a d gamma. Okay, so gamma is our symbol for the decay. So let's write it down. So decay, I have a 1 particle in the initial state. That will be 1 over 2 EI. So it enters the initial state. And then I will have a transition amplitude of 1 to NF square. And then for each, and then there's a total momentum conserving delta function, and then for each final state particle, we have this EF. Okay, so nothing new. I just use the fact I just have a single particle. That's all. Now, again, this is my PF. Let's actually first check the dimension of this quantity. Okay, so let's actually check the dimension of quantity, mass dimension of this quantity. So you can ask, what is mass dimension of gamma? So we can break it up. So first of all, what is the mass dimension of a DF? Let's see. So there's this overall momentum conserving delta function, which is -4. And then for each final state particle, I have a power of 3 in the numerator and then 1 power in the denominator, so it's dimension 2. So this thing is going to be 2 per each initial final state particle, and then 1 overall momentum conserving delta function. So that's the estimation of this that set of state. Now let's think about the dimension of this amplitude. So what's that? So in order to figure out this, 1, 2, and f. So let's go back to the definition of how that was defined. Okay? So how that was defined? Well, that was defined as follows. There's a final d, and then s minus 1, initial, okay? And then this was related to, well, maybe there's factors of I, but that doesn't matter. Momentum conserving delta function. Remember, this can be written as, so s can be written as 1 plus it, and then we define as I momentum conserving delta function times, if I sandwich it, sandwich it understood, there's an amplitude, right? So that was the definition of invariant amplitude. Good, so then I have this amplitude. But be careful. So this 9 definition is in terms of what? Relativistically invariant normalization. Okay, but I'm using this. So I need to use the conversion factor to remember for each final state, I had a square root of b, square root of 2e. Right? And for initial, I had this, and then square root of b. But since I have a single guy, I don't need to worry too much about it. Okay, but that's the definition. So since we are going to figure this out, let's just do it in general. Okay, let's just figure out the dimension of amplitude in general, considering both the case where initial number of particles is either 1 for the decay, and then initial number of particles 2 for the scattering, which we will also use for the discussion of scattering. So good. Now, what is the dimension of this stuff? So when Ni is equal to 1 for the discussion. Remember, S is dimensionless. This is e to the minus, this is basically e to the minus I integral over the HI. Okay? Or 1, so it's a dimensionless quantity. Final state, with this factor probably in for every particle in the final state, it's a dimensionless quantity. Okay? Right? So this is dimensionless. So for initial, if I talk about the single particle case, it's as if I'm just multiplying correct conversion factor, so it is dimensionless. So for one particle in the initial state, this entire thing is 0, dimension 0. 0, 0 always, but 0 for one particle in the initial state. Okay? So that is equal to minus 4, and then this. So what about this? So this is 3/2. The volume has a dimension minus 3, so square root of 1 over. Okay, and then this is minus half per each final state particle. And then for initial particle, so what's that? So that's minus half, and then 3/2. So this tells me that for decay, 1 to NF, the dimension of amplitude is, that's 1 times NF, 4, that's 1, 3 minus NF. Okay? So that's the answer. What about if I talk about the scattering? There are 2 particles in the initial state. Remember what I wrote here, right?